Welcome to ihnani.com. Computer Programming. Level 2 Bytes. Bits and bytes. If you have completed our Computer Fundamentals Part 1 and 2 videos, then you have heard the words bits and bytes. Computer memory is measured in bytes, as are file sizes when you examine them in a file viewer. Whenever you go to purchase a computer, you might have read on the configuration sheet, or heard the salesman saying, that the computer contains so many gigabytes of RAM, hard disk space, etc. All these are measured in bytes, which are termed as kilobytes, megabytes, gigabytes, terabytes, and so on. This does not mean that bytes are the smallest possible data measure. That crown goes to bit. What is a bit? A bit is the smallest possible piece of information that a computer can make use of, or store. Whenever I used to say that computers can only understand ones and zeros, I was actually referring to bits. In other words, a bit can also be defined as a variable or computed quantity that can have only two possible values, which are often interpreted as binary digits, and are usually denoted by the numerical digits 0 and 1. In fact, the term bit is a contraction of binary digit. The two values are also interpreted as logical values, true or false, yes or no, algebraic signs plus or minus, activation states, on or off, or any other two-valued attributes. They all mean the same thing, to say that there are only two possibilities, and nothing else. All of the information that is stored in the computer, or travels through a computer, is based on these bits. But it's hard to imagine, since you have used computers for various other complex operations such as browsing the internet, watching movies, listening to songs, working on documents with text and picture content, and a lot more. You might have also heard people talking about the absolutely complex calculations that computers do, involving massive numbers. But all those huge numbers, they're just made up of zeros and ones. In order to imagine how these zeros and ones are stored or transmitted in a computer, think of a light bulb kind of a device inside the computer, but it is so tiny that you can't see it with bare eyes. When this bulb is on, it represents 1, and when it is off, it represents 0. We can in fact tie these bits to the punch card technology that was pioneered by Joseph Marie Jacquard in 1801 in his invention, the Jacquard loom. The idea behind the Jacquard loom was a system of punch cards and hooks. The cards were made very thick and had rectangular holes punched in them. The hooks and needles used in weaving were guided by these holes in the cardboard. When the hooks came into contact with the card, they were held stationary, unless it encountered one of the punched holes. Then, the hook was able to pass through the hole, with a needle inserting another thread, thus forming the desired pattern. Intricate patterns were achieved by having many cards arranged one after the other, and were used repeatedly. This idea of punch cards was revolutionary, since it used the idea of a machine having the ability to follow an algorithm. These punch cards were innovative, because the cards had the capability to store information on them. This ability to store information was what helped spark the computer revolution. With these punched cards, it is the hole that can be compared to a bit, with every point containing a hole to be on, and without it to be off. The next major invention was the vacuum tubes, a fragile glass device that used filaments as a source of electrons and could control and amplify electronic signals. It was one of the high-speed electronic switching devices available, at that time. Though the punched card idea did use the on and off concept, it is these vacuum tubes which can be considered as their real contender for the electronic way of storing data. Transistor, a device composed of semiconductor material that amplifies a signal or opens and closes a circuit, replaced vacuum tubes. A transistor is far superior to a vacuum tube, while their size was reduced drastically when compared to vacuum tubes. The development of the integrated circuit was the hallmark of the third generation of computers. Transistors were miniaturized and placed on silicon chips, called semiconductors. A typical chip is less than quarter square inches and can contain millions of transistors. For more details on punched cards, vacuum tubes, transistors, ICs, check out our tutorial Computer Fundamentals Part 1 and 2. Now, let us get back to know how bits are maintained in a computer. If you have already finished our tutorial on Computer Fundamentals Part 1 and 2, you will know about the electric power supply that is inside the computer, and how it sends electricity to all of the components. That electricity is what creates on signal. The memory chips in a computer are made up of millions of tiny compartments called transistors, which is what we refer to as bits. With electricity, transistors can both switch or amplify electronic signals, letting us control the electric current that moves through a circuit board with precision. In simple terms, transistors can be used to turn current on or off in a circuit as an electrically controlled switch, where the amount of current is determined by other circuit elements. The computer reads on as a number 1 and off as number 0. Now this is how we have a bit. We hope this gives you sufficient information on what is a bit and how it is stored inside a computer. In case if you have any questions or need more information, please use our forum. We will be glad to help you out. What is a byte? By definition, a byte is a unit of digital information, in computing and telecommunications, that most commonly consists of 8 bits. Just by having 0 or 1 wouldn't have made much of a difference, but if we take a sequence of zeros and ones, we can have a combination, and when we assign each combination to a number, character or a symbol, then it will make sense. 8 bits are grouped together to form a byte. In this group of 8, there are 256 possible combinations of zeros and ones. The grouping of zeros and ones within a byte is called binary code. Bits are practically always bundled together into 8-bit collections, and these collections are called bytes. Put in very simple and common terms, 8 bits in a sequence is known as a byte. You may now have a question. Why are there only 8 bits in a byte? This is something like asking, why are there only 12 in a dozen? Historically, the size of the byte has been hardware dependent. There is no conclusive standard that mandates the size to be just 8 bits. The popularity of major commercial computing architectures have aided in the universal acceptance of the 8-bit size. There can be a total of 256 combinations from these 8 bits, and can therefore, each of these combinations can be assigned to a variety of different symbols, letters or instructions. ASCII is one of the standards for character encoding schema. ASCII stands for American Standard Code for Information Interchange. Why should they be in a sequence? Let us take 2 different combinations of bits and their ASCII characters. 00110000 represents the ASCII character 0, while 01000001 represents uppercase A. If you monitor the above two bytes closely, you can see that, in both these combinations there are 6 zeros and 2 ones. While the first sequence of binary digits is assigned a value 0, the second sequence of binary digits is assigned a value of A. The only difference is that their sequence. While in the first sequence, the third and fourth digits are ones, the second sequence contains the second and the eighth digits as ones. In this example, you can find out why it is so important to have the bits in a sequence, and not just in any order. A computer can understand only zeros and ones, which we can't. A sequence of 8 bits make up a meaningful character for us, but without any sense. A few bytes can make up something meaningful to us. For example, check out these bytes. Does it make any sense to you? For me, it's nothing but a set of zeros and ones and nothing more. Now, if we replace the first byte with its corresponding ASCII character, we get uppercase H. Though we can understand or read this alphabet, it doesn't make any sense on its own. If we now replace the remaining bytes with its corresponding ASCII characters, we get the alphabets H, E, L, L, O, and when we read them together, we get the word hello. Now this becomes a meaningful word. A few millions of zeros and ones, given in series, is what makes a computer work. Fundamentally, computers perform operations on groups of bits. A microprocessor, which processes these groups of bits, though is very primitive but is very fast. A CPU takes groups of bits, does some calculations, adds, subtracts, divides, multiplies, and whatever it asked to do, and returns the result, which is then converted back into human understandable form. But at the lowest level, everything is simply a bunch of bits, things that are either on or off. In this video, we just covered quite a bit on zeros and ones that a computer can understand. In the third video of this tutorial, Computer Programming, Level 2, let us explore on how these bits and bytes work. You can find a lot of free video tutorials, training materials, how-to videos and much more at our site www.inani.com. Check out the forum topic related to this tutorial.